We are going to start at section 9.2 direction fields. I think I went over them far too quickly, and I want to make sure that we're good at them. So we're going to show you, and there's a lovely piece of software that's going to make this 10 times easier as well. So I want to go into the details of that software that I've got. So we're going to look at direction fields, and then we'll start our next section, 9.3, and that is on how to solve differential equations. So we're actually going to finally get to solve a differential equation. So let's look at what 9.2 is about. It's called direction fields. Well, a direction field, one of these is going to become it, is a diagram that allows you to see, right, to visualize a differential equation. So imagine you've got this very simple differential equation that the derivative of some unknown function is equal to x plus y. So you would take randomly, you would take some points. So you might, for instance, take the point 1, 2. And at that point, according to this, the derivative would be the x coordinate plus y coordinate. It would be 1 plus 2, that's 3. And so you go to the point 1, that's x1, y2. You go to the point 1, 2, which is here, and you draw a slope that's 3. Can you imagine that's a slope 3 units, right? That's a slope of 3. Now, I'm not going to do it to all of them. That's pretty bad idea. But for instance, if I did this point, the derivative, which is the x plus the y coordinate, would be 0. So at the point negative 2, 2, which is what, here, it'd be sloped. It'd be horizontal. I'll do just one more. Where shall I do? I'll do it over here. And suppose you do 2, negative 1. Actually, I just decided to do one more. You get 1. So at 2, negative 1, which is here, you get a slope of 1, which is about that slope. And one more, because I need to show you something that could harm. How about negative 1, negative 1? Well, if you did that one, you get negative 2. So at this point here, the slope is negative 2. Now, can you imagine me going through all, whatever it is, 30 points, doing this calculation, and my best guess at drawing the line, right? And the slopes would be 0, minus 1, minus 2, plus 2, and so on. This guy would be horizontal. This would be steep. This would be steeper, and this would be almost vertical. This one would go down a little bit, go down a little bit more, be horizontal, then it would go negative on you. This one would be horizontal, up a little bit steeper, down a little bit steeper. This one here would be horizontal. This one wouldn't be quite as negative. Actually, this one would be horizontal. This one here would be very negative. And this here would be slightly positive, almost finished. 0, it would be, what would that be? This one here. This one is not, this one. I like that, 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 right. A real pain in the butt, agreed, and nobody wants to do them by hand. So we don't. So that's how you would create one by hand. You'd go through all 30 points, find out what the slope is, and try and draw a line equal to that slope. Instead, what we're going to do is use some software, and I want to spend a little bit more time on that to show you how it works. So you should be looking at our, well, it's actually the other classes, so not that matters, but let's get the right one. Here we go. You'll be looking at our class, and if we hit this fella, graphing direction fields, this is the software. Now, can you see that I've already typed in x plus y. So it doesn't say dy by dx. It says f dash, but it's the same thing, right? X plus y. And that's what the pattern would look like. Now, quite a lot of homework questions say to you, draw the curve where y of 0 equals 1, right? Y of 0 equals 1 means the x coordinate is 0, the y coordinate is 1. So that would end up being the point 0, 1. So you click on this guy and you see the little dot there. If you keep your mouse on it, you can move it to 0, 1. Yeah. Can you see what the curve would look like now? Rather than me trying to do it by hand and making a mess up. Now, suppose you had to do 4 points. Suppose the next one was at y of 0 is 0. Suppose the next one is y of 0 is -1. And suppose the next one is y of 0 equals, I know, let's make the number a little bit different, -3. Can you see that what you now have is 4 possible particular solutions to the differential equation? You can visualize it in different ways. Can you imagine that there's a little boat, this is a current on some river, right? And there's a little paper boat dropped into it, and you just watched the paper boat and you've seen what it did, right? So if you dropped the paper boat here, do you see that it would travel like that? If you dropped it down here, do you see it would still travel like that? Do you see in this particular case, all pathways lead to this line? You see this line going diagonally like this. That is called that particular one is an equilibrium solution. If you're interested in the name, it's called an equilibrium solution. So let me jump into, no, try this page. Yay. Okay. So let's show you an example of that question. This question too, well, I can, if I make it big, you won't see all the diagrams, but that's fine. You can't get everything. There we go. dy by dx equals 6 minus y. And there are 4 pictures there it could be, right? 4 pictures it could be. So you go to that piece of software that I was using a few minutes ago, this one here. I'll click off these guys. And I like this piece of software better than the other one. And you just go up here and you can do 6 take away y. So when I click off it, there. Now, do you see that is quite a different looking direction field? So if you can visualize what this looks like, if we now return, no, it's on my different windows. God, I need new eyes. Is it this one? Of course, I had to pick all 3 before I found it. One of these guys looked like our guy. You see it, 6 minus y. So it's those 4. There's the guy. Well, it kind of comes up and it begins to curl. So it kind of goes up and then it begins to curl. And it looks like it could be this one here, right? So let's see if I can make it a little bit more obvious. It looks like in this picture here, they go all the way up to 12. Well, I would like to know what it looks like if you go all the way up to 12. So I'm just changing that to 12. Boom. And looks like that, but it doesn't. Why aren't you changing? Oh, there we go. There, can you see it now? I had to shrink it up to see it, but it does go up to 12. So it comes up and then it kind of zigzags in. So hopefully that's enough to get a picture. I think it's this one. No. This one. There we go. believe it's that one.
Is this something we might see on an exam?
This is dead easy to do in an exam.
I'm just wondering, how would we show our work to prove to you that?
You wouldn't.
Okay.
This would be so easy. You just tell me it's picture 2 and move on. So in a funny sort of a way, it's an easier exam question. Right, let's do this one because it's got more. Right, x 8 minus y. Right, I'm going to have to do some there. I'm putting them on different windows because it's really difficult for me to jump between the two. 8, take away y. Click out of it. Just return this to 5s. We're good. There we are. So evidently that's what 8, oh, it's not. It's got an x in it as well. Well, that's easy to do. X brackets 8 minus y. There we go. Pictures I'm looking at go from 0 to, well, they don't, they go from all sorts of different places. Right, there's the thing. It looks like it's mostly verticals and then it curves away. And the picture that looks like that, I think, is the second picture. If I show you the screen, then I have to show you the other thing. And I think this zooming back and forth is causing me more hassle than it's worth. So I'm going to make up one last one. Let's suppose we had a guy that looks like that, which is interesting. And I'll open up these windows to different values as well. There we go. There, I've got a pretty decent looking one. I could shrink it back a little bit. There we go. And if you did this one of the 4 pictures would match it. What I can see that's interesting, do you see over here, there's a little weird kind of difference thing going on that the others don't seem to have? That would be a feature that I would look for. And suppose I wanted to do a solution, right? If y of 0 equals 1, it would be this graph. If y of 2 equals 0, well, make it number 5, it would be this graph. You see, I can move this fella along and you can see, well, there we are. Oh, that's kind of interesting. See that little funny little kink there? Put another one and see if I can surround it. Put a third one in. Can you see there's some really weird happening around about here? It's fun. I got distracted. So essentially for direction fields, if you use this software, your life will be a lot quicker. So I'm now going to not look at the software anymore. We're just going to show you the questions and how you would tackle them. I think that way might make my life a lot easier and yours as well. Right, so in this question, here is the differential equation. Figure out which one of these 4 pictures it is. And then you can pick one of the reasons for it. Right. Oh, this has got all the solutions on it, which is very distracting for me. Right, here is a direction field. Y of 0 equals 6. Now, what's different about this one? They don't have a formula, so you can't do the software, but we can use this because it's already given. Y of 0 equals 6 means when x is 0, the y is 6. So that's about here, right? You see my mouse is pointing roughly at 0, 6. Now, if you were at that point, can you see that the slopes are taking you like curving up this way? And then if you go the other direction, they're curving you up that way. So what I would say this looks like is a happy face. round about 6. And would you agree it's that one? Now, the next one is 0, 0, which is the origin, right? So if you're at the origin, which is there, do you see that you're probably going to shoot along this line and shoot up that line? So that would give me that fella. 11's back to, here's the software, type that in. You will get this picture. And then you can do this 0, 1, 0, -1, 0, -3, and 0, 3. Now, if you do that, one of these 4 pictures here will look like yours. And I don't know what it is, so I am going to say it's that one just to get that question done. And then it says find the equilibrium solution. So if we go up here and you look for any place where things would be captured, y equals 2, y equals -2. And you're done. And to finish with, here is the function that you put into the software. Here are the 5 guys that you would use. And one of these would be your picture. And it reminds me of Mick Jagger's mouth. I don't know what it reminds you of. Nobody knows who Mick Jagger is. Okay, I'm showing my age again. All right, I hope that has helped, because the reason I wanted to do that is that we do have quite good software. It's the kind of thing that if you play about with it, you'll be able to get a lot of benefit. It does pretty much all the hard work for you. So we're now moving on to section 9.3. This is the main section. This is one of 2 things that are probably the most important in chapter 2. And there's this one, and the other one's going to be solving linear differential equations. So this one is variables separable differential equation. We are going to learn how to solve a particular kind of differential equation. Let's show you what it looks like. Excuse me. I will do that. There we go. So back to our thing. So a first order differential equation that can be written in the form dy by dx, and it can be written as a fraction where everything on the top has x's in it and everything on the bottom has y's in it. If you can get a differential equation and rearrange it so it looks like this, we call these differential equations variable separable. And there is a way that we'll show you today on how to solve these. So let's just show you some examples of what would qualify. X squared plus x minus 1 over sine 1. Do you see that's got the right shape? It's a fraction, right? Functions, numbers count, right? X is on the top, y is on the bottom. Doesn't need to be x's and y's. It could be what? T's and y's, right? Are we comfortable about what a variable separable differential equation looks like? Now, your life's dead easy because in section 9.3, every single one of them is variable separable. But in the big picture, isn't it useful if you can tell when one is and when it's not? So let's look at how to solve them. Okay, we'll start off with nice simple ones before we get. There is our first variable separable differential equation. Now, the way that you solve them reminds me of cross multiplication. What you do is you go this way and you go that way. Can you think U subs? Don't you do a similar looking thing when you do U subs? Remember my crossover in U subs. Now you might say, well, how's that going to solve anything? You stick an integral in front of it. So you do a crossover integral. Looks very like cross multiplication to me, doesn't it? It's not, but it looks like it. And then you integrate this guy and you add 1 to the power and you get what? Y cubed. And you get 1/3 x cubed. You get 1/2 x squared plus an arbitrary constant c. And you only ever have 1 plus c. And you either give it to the left or the right, but here's the convention. Always give it to the x's, the guy on the right. Now you may say, but why do I only have 1 plus c? Surely there would be one here and there'd be another different one here. So pretend I did that and we'll show you why you don't need it. So c plus d, 1/3 x cubed plus 1/2 x squared plus c. Couldn't I subtract the d from both sides? Now, if you think about it, isn't c minus d just a number that you don't know? Isn't it just an arbitrary constant? Right, you don't know who c is, you don't know who d is, so you definitely don't know what c take away d is. So it makes sense that you could just call it c. Or if you wanted, I'll call that b, and that's b minus d, and now I'll call it c. But are we cool with that? You happy with why there's only 1 plus c? I don't see any thumbs up today. That's not a good sign. You're not happy with it. Can you live with it then?
I know D anymore. Sorry.
You don't need any d's. You only have 1 arbitrary constant. Put it there.
Work.
Now, sometimes you're finished. Sometimes when you do these equations, solving these variable separable differential equations, you get y cubed plus sine y plus e to the y, and you get a whole load of x's over here. There is no way in the world you'll be able to transfer that into a single y equals. But there's quite a few times where you will be able to get this to be y equals. In this case, this is one of those situations. So what would I need to do to both sides to go from this line to y equals?
Cube root.
That's it. Just stick everything inside the cube root. And we have just solved our first differential equation that was variable separable. Do a crossover, integrate, make the answer look pretty. Because this has got a plus c, this is called the general solution of that differential equation. But it's not that uncommon that you get told something like this. Right, you get added in some of the later questions, they tell you that. Now, this has got a name to remind you what they were called. It's called a boundary condition. It's also called an initial condition as well. That's another name for it. Right, suppose this question had that. This has one job and one job only. Isn't its job to tell you what C is? So if you tell me that when X is 1, Y is 2, I'll put a 2 there. I'll do a cube root of 1/3 times 1 cubed, 1/2 times 1 squared plus C. And I will be looking at 1/3 plus 1/2, which is 5/6 plus C. Now we want to solve for C, so I'll take a couple of lines. What's the first thing I'm going to do to both sides?
Cube.
Correct. 2 cubed is 8. Then I'll subtract 5, 6 from both sides. So I'm going to have to call that, I'm going to have to call that 48, 6. Take away 5, 6 leaves you with 43, 6. Not the prettiest C in the world, but it'll have to do. That means that we now know the solution in all its entirety. And this guy is called a particular solution to the differential equation, right? So when there is no plus C's left over, you have got a particular solution. Now, if you went to that software and you typed this in, and then you went and chose the point x1, y is 2, you'd see some green curve. The equation of that green curve is this guy here. So that's what you were finding in that software, where you went and put a little dot at 1, 2, and you saw where it went to. You're basically finding out what the particular solution to the differential equation would look like at that one particular space. Are we good? So I am now going to open up. You won't see it, but nonetheless, I should be able to do it. Yeah. I'm going to open up our software to 9.3 software and pick some questions. Now, it doesn't take them too long to start making your life a little bit more difficult, especially algebraically. So here is right out the bat, a question that looks like number 1. You got this guy, 3x squared, y squared. So right away, we have a major problem. Doesn't this have to be written as a fraction? And doesn't it have to be x's on the top, right, and y's on the bottom? This guy doesn't look like a fraction, but it has to become one. I like the 3x squared. What can I do with this y squared? What will I call it if I bring it downstairs?
Y to the -2.
Yeah. Have you ever seen that trick where a positive power on the top can be written as the negative power on the bottom? Right, it's an algebra situation. Now, this guy is good to go. The crossover integral looks like that. Power rule, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power, and give this guy the plus C. So far, so good. Now, if you can write the answer as y equals, you're expected to. So you might say to yourself, how do I know when it's possible? This is how I tell. If the left-hand side only has a single y, no matter how weird it looks, no matter what it is, if there's only one y present, then it should be doable. You should be able to rewrite it eventually as y equals. So I'm going to take this very slowly and multiply both sides by -1. I'm then going to call this guy 1 over y. If 1 over y equals this, what will this equal?
One over negative x cubed minus c.
And you have now finished the question. Are we good? First one, at least? Right. Each one I do tonight is going to get, probably for most of them, uglier and uglier and more, fiddly, right? So keep that in mind. This one is a version of question 3. I'm writing it down the way that it is written, just so you get familiar with it. You can't use y dashed. You have to call it dy by dx. Does that make sense? Just because the way the process works, right? I need a y and I need an x, right? I need a dy by dx. So anytime you see a y dashed, write it down like that. Now I'm going to subtract, while I'm at it, that guy from both sides. Now, we've already kind of met this problem before. It seems to be a common theme, at least in the early questions, that we don't have a fraction. So how are we going to do e to the y? How are we going to fix it? Come on, you know the answer. Just tell us, get over with.
Y.
E negative y, okay. Right, you do the crossover and integrate. That pretty standard. Depends what you get, what you do next, but most of the time it doesn't seem to be too difficult. A power rule with a plus c. Be careful. If you integrate e to the negative y, you do get e to the negative y, but you also get something else, don't you? What's missing?
Would it be dy dx or?
Nothing as messy as that. Something much simpler.
Just a -1?
Yeah, that's all. Okay. Now, multiply both sides by -1. Oh, now things get a little bit trickier. There is a y here. That means I should be able to rewrite this as y equals, right? So we need to figure out how that's going to happen. Any ideas how you would make that happen?
Natural log.
Now, if you take the natural log of this side, you get that. And if you take the natural log of the other side, you get that. Do you see how much algebra is going to be involved in these questions? Now, I don't know how long ago it's been since you did this, but it's important that you know. Now, you get y, there you go. And we are now finished. There's your general solution. Now, side note. That is also a solution. This C is not the same guy as that C. Don't think of C as a fixed thing. Think of C as a placeholder, right? It just means there's a number in there, you don't know what it is. If you don't know what it is, isn't minus something you don't know what it is the same thing as plus another thing that you don't know what it is? Now, the reason why I want to be kind of emphasizing this is that that is actually much more common in most textbooks. So if you go and watch a video, you might well see this becoming that, and you think, what on earth happened to that negative C? It's now a plus C. We tend to like to write equations with a plus C. Don't they kind of look prettier? Also, can you imagine a question where you had to multiply both sides by 2, then you had to divide everything by 3, and then you multiply by a negative as well, you could end up with a negative 2/3 c, couldn't you? Well, why don't you just call it plus c and bite the bullet? Because isn't negative 2/3 something you don't know the same thing as something you don't know? So just call it plus c. So that's much more common. But to keep WebAssign happy, this is the one you're going to have to type in. Let's move on. I'm going to assume that if things aren't good, you will just give me a shout out and say, hey guys, that didn't make sense, or could you go over line 4 again? No. This one is like jumping off the cliff in Hawaii and hoping you don't hit your head on the rocks. Watch this one. That guy does not look even vaguely variable separable, especially the bottom. Agreed? But it is, because every question is. We don't need to, you know, decide. Every question in this section is variable separable. Is there anything algebraically you can do with the bottom? Is there anything style points that you might want to do? You don't see anything here that can be factored out, for instance. Okay,
Factor out a u and a t squared.
that's good. And that is correct. And I'm not writing it down, but that's okay. That's just me. Yeah, well, that's good. The reason I didn't bring out your U is I'm just trying to keep it tidy. Nothing wrong with you. It's a good answer. Now, what's going to happen to this fella? Whoa. Well, it has to be a fraction. And it's going to be u plus u to the 4 on the bottom. Because in this particular situation, you know, think crossover. Isn't, if the u's here, the u's have to be in the bottom. Doesn't that make the t's have to be in the top? Now, if t is on the bottom and you bring it to the top, would you agree that it becomes -2? And just to finish, do you see that we now have finally got variable separable? Now that will, other things will happen to that, right? So if you're writing notes and you want to keep the notes, you'll need at least another full page, right? A whole page like this and that to do it. But I'm not going to do it yet because I want to spend just a little bit of time in doing the variable separable thing, right? So that we can get practice at the algebra. Because I think if we keep that together, it might help us see what's going on. So I'm coming back to 4, but you'll need to put a few bits of paper to finish off the question. So I'm just warning you, leave some space. Right. This is like question 5. And we have this fella. Now this is eventually going to be a fraction. But before I even think about that, do you notice that I've split the e to the t plus z into e to the t times e to the z? Because if you multiply these two, don't you add their powers? Now, the reason I would do that is that I can now get my fraction. So do you see how that one was tackled? How we got the variable separable out of that one? This one, when we come back to solving it, probably won't need any more than about the amount of lines I've got here. So you can keep that on one page, probably. This one is like question 11. Okay, we need to get variable separable out of this one. The first thing I'm going to do is split apart the two square roots. Then rewrite the square roots as half powers. And finally, do that. So do you see that there's a lot of variation on how you would get a differential equation and rewrite it in its variable separable form? This one would probably take about a page and a half to do. Do you feel comfortable about how we had to tackle different situations, how we got them into that separable fraction format that we need? Okay. So if that's the case, let's return to what is probably the ugliest and hardest one in the entire section. So we can do this one. We're going to have a lot less work to do in the others. So I got this fella. And I got this fella. Are we good? Actually, I take it back. It's actually turned out a lot nicer than I thought. I didn't really realize that until I did this. Add 1 to the power, divide by the new power. And the reason why is I just realized I can't fix that. Would you agree it's impossible to rewrite that as a u equals? Right. There's no algebra in the world that would allow you to convert this expression into a u equals function of t. And in a funny sort of a way, that's actually good news because it means the question's finished. I thought originally that this could have been a single value and then I could have, done about 10 lines of algebra just to make it happen. But actually, it's not as bad as I thought it was going to be. And that's not a bad thing. So, questions over. You basically type that in. Analogy. Way back in Calc 1, you came across functions, curves that look like that. The most likely one that you actually came across was x squared plus y squared equals 9. They're called implicit expressions, right? Implicit graphs. The x's and y's are all jumbled up, right? this here is a bit like a half y squared plus 1/5 y to the 5 is equal to 4 of this plus a third of this plus 5 or something. This is fine. This is implicit. So it's not normal you would expect mathematicians to leave something ugly, but sometimes you just have to. This fella. You do the crossover. I don't think this one's going to take too much of our time. Remember the negative. Multiply both sides by -1. Take the natural log of both sides. Now notice the natural log is of the whole package. It's not the natural log of this, take away the natural log of that. It's not separated. It's one single natural log. And you're finished. Now, oops, where is it? Right, can't find it now. Oh, here it is. And here is the one called 11. And I just noticed something that's wrong. This, although it is a fraction, is the wrong fraction. Shouldn't there be t's on the top and p's on the bottom? Right? P's on the bottom, t's on the top. So that guy, I like to keep the numbers on the top. And that guy, right? That's the one I should have had. So now I can do the crossover. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Are we good so far? Do you notice that there's only a single p on the left-hand side? That means this question can be rewritten eventually as p equals. Any suggestions for what we should do next to get closer to that place?
Divide both sides by 2.
Right, now if you do that, you're going to have that. Agreed? I'm just checking what they have done with the C. Oh, they copped out. They totally copped out. According to what I'm looking at, they just left it like that.
For the
No.
bottom part, would you still have p to the 1/2, or how would that work?
Oh, yeah, that would be p to the half here. They totally darn it in space. I don't like that. I'm doing this question not the way they've got it, because that is just bad math. Would you agree that this can be turned into P equals? There's no reason in the world you should leave it hanging. Agreed? So, divided. What am I going to do next to get P? If it helps, isn't...
Square.
Yeah, you square it. Would you agree that was not a major issue? I don't see why they avoided it, but who knows? Sometimes people make mistakes. That is just bad math. This is good. I like this one. Me personally, I think that looks prettier. If you don't know what it is, you don't know what half of it is either, do you? So I might as well just call the whole thing plus C. I wonder if I can type in that answer. I want to check that. I'm not really able to do that. No. Okay. This question had an added bonus. They told you that. Which means that when T is 1, P is 6. So I should be able to find out what C is, and we should be good to go. So P is 6 when T is 1. So it's going to be 8/3, well, basically times 1, add C squared. So square root of 6 is 8/3 plus C. That makes C square root of the square root of 6, take away 8/3. And so P will be 8/3 T to the 3/2 plus C squared. Which is kind of ugly, but that's what the answer would be. Okay, so apart from being a bit annoyed about the answer to the first part, the second part comes out exactly the way it should. So I guess I shouldn't be that annoyed at that. Well, I think we should give you one to try, because that's always the best way to figure out, do you know what the heck is going on? And since I haven't done a trig one, dy by dx is equal to 2x plus secant squared x u squared. Okay, your job is to solve this differential equation, and you have got 3 minutes to have a shot at it. So go for it. And from time to time, I will add little extra lines if you've sort of got stuck. For those who are stuck on the beginning, that's how you get the fraction. And I apologize. Last few seconds. Okay, you've got this guy. Bring this downstairs. Make sure the diagonal thing fits, which it does. On this side, you get y to -2. And this side, you got all the x's. Add 1 to the power, divide by new power. We've seen that before. Okay, this is just memory work. What is the antiderivative of secant squared?
Isn't it like 1 minus tan squared?
That's a identity that you would turn it into, but that's not its integral.
Tan.
Tan. And give this the plus c. Right, to finish it, you should realize that this can be written as a y equals, so multiply everybody by -1. And to keep Weber sign happy, we'll call that minus c. We had a question earlier today, which was very similar looking to this one. And you're finished. So hopefully you got a question like that. You managed to do it. So where am I off to next? There's a log one somewhere. I want to find it. You can never see it when you need it. Oh, let's do a second part to this one. Let's suppose I tell you that y of 0 equals 1. Now, if you're doing that, won't you now be able to find c? So let's see how that works. When x is 0, the y is 1. So we have this guy. And he's equal to 1 when x is 0. So minus 0, tan is 0, plus c. So basically, you're trying to solve that. That's so easy, I can just do it in my head. And so your particular solution so there's your particular solution to differential equation. And this one is your general solution to a differential equation. I hope the more of these that we do, the more comfortable you are in working with them. Right, now, Let's go in for that log one I saw earlier because it looked interesting. Where are you hiding, log? Must be down the bottom. How about that? Here we go. The L dt is k L squared, the natural log of t. You've been told that L of 1 equals -6. Now you might be thinking, I hope you are, what's that k? That k is a constant. So you're just going to pretend it's 2, but write down k. And it's not uncommon for a differential equation to have a letter in it, a constant like this. If you try to do Hooke's law, remember Hooke's law way back in the day? It came from a differential equation, and k in that world was a number that's associated with how strong the spring is. So I'm going to turn this guy into a fraction. And I realize that the t should be on the top. And I'll give that the k. And the L should be on the bottom. There we go. Are you happy with the transformation, right? Bringing somebody into a fraction by making a negative power. So when we do the crossover, we get that. If you integrate this guy, add 1 to the power, divide by the new power. Oh, if you integrate log t, or log x, or log y, or log any letter of the alphabet you care to use as a variable, if you've already got a guy like this, and you write down guys as you find them, can you remember we did integration by parts to find out what the integral of that fella is? And the answer is it's k t log t, take away t. And the k goes here, plus c. So that guy is x log x minus x, but since we're using t, it's x log t. Sorry, t log t, take away t. So I'm just going to rewrite that a little bit differently. kt ln of t, take away kt plus c. Then I'll multiply everybody by -1. Saying this about 3 times. I'll rewrite the -1 power as a fraction. And that way it might make it easier to see. Oops, so minus c. And if all they wanted was the general solution, we are done. But they told us that. So we are now going to find c. So L is 1 over -kt log t plus a kt, take away a c. And we've just been told by that boundary condition that when t is 1, the L is -6. So I'm going to put a -6 here. And this is going to get replaced by 1. So -k times 1 times the log of 1 plus k times 1 take away c. Now the log of 1 is 0. So all we get is k take away c. And then you might get a little bit confused and say, what am I trying to find here? And the answer is you're trying to find out who c is. So I would cross multiply. And that would be negative 6k take away c is 1. That's negative 6k plus 6c is 1. That makes 6c 1 plus 6k, and that makes c 1/6 plus a k. And then you can put it up here. So L is 1 over, and I'm going to do a deliberate mistake here. Kt log t plus kt plus c. And what is the deliberate mistake that I have made? Anybody see it? Maybe it's just staring you in the face and you're not noticing it because it's not sticking out.
Is it the 12T?
Nope. Do you notice this thing here? Doesn't it say minus c? Now, if I know what c is, shouldn't this be minus c? So it's all of this, take away c. Not add c, but just take away c. And little mistake like that. And the reason why it's there is, look at that formula. Do you see the formula has minus c, not plus c? Do you know if that said minus 2c, wouldn't I stick minus 2 times that there? Okay, what's left? Here is an application called population models. A way back in Math 141, do you remember getting formulas for population growth models that look like that? Good, someone remembers it. So what we're going to do is we are actually going to generate a differential equation for a population model just like this, solve it, and prove to you this is what we get. Now, there are two numbers in these. The population at time 0 is 200. So in this story, the initial population, sometimes they use that exact term, that the initial population of a town was 200 people. So it's a tiny little town in the desert. This fella here, right, is called the rate of change. So in this case, the rate of change was what? 10% written as a decimal. So what we have here is a town that starts with 200 people and it increases at the rate of 10% a year, right? So there's 10% more people the next year compared to the last year. So let's show you how that would become a differential equation. The increase in people, that's what that is, right? The rate of increase is 10% of the population. So the rate of increase is 0.1 times p. That's essentially what this is saying. And the population at time 0 is 200. So that's going to be my boundary condition that I'll use later on. So I'm going to take this guy and I am going to make him or solve him as a variable separable. And sometimes the simple ones can catch you. This has to be a fraction. It isn't much of an expression. 0.1p doesn't have a lot going on. but it has to be a fraction. And doesn't the p have to be on the bottom? Now you might say, well, what about the t? It don't matter if there isn't a t, it's still a fraction. We can still use variable separable on it. So are you okay about this becoming that? And do you notice I want the p's on the top and the other thing on the top? B's p on the bottom and the other thing on the top. So when we do our crossover, we get that. Now this guy is easy. This guy is not, because writing them as that power doesn't actually help me integrate it. Because isn't p to the negative 1 a special situation? It's the same thing as 1 over p. And when you integrate a 1 over p, you get a natural log. What do I do to both sides to get p on its own? Any suggestions? What could I do to both sides to get p on its own? How about raise both to the power of e? E to the natural log of p is p, and it's going to equal this guy. And we have now got the general solution to our population model. Now I'm going to bring in this fella. When t is 0, p is 200. So I'm going to put 200 here, e to the 0.1 times nothing, add c. 200 is equal to e to the c. If you want to get c, take the natural log of both sides. Which means our population model is now 0.1 t plus the natural log of 200. Now you might say, hey, wait a minute, that's not the answer it should be. Well, let's make it the answer it should be. You can separate this out into that. And isn't e to the natural log of 200 just 200 and you stick it in the front? So we have just created from scratch the exponential model that you get told or you worked with in Math 141. It's pretty clever, I think. Any questions about that before we move on? A very quiet lot today. I'm beginning to feel I'm on my own. It's not a nice feeling.
Maybe everybody's just tired.
Oh, I can understand that. I mean, it's a long day for everybody, and I hope you don't feel I'm getting at you too much, but I understand. Okay. The next question I want to do is a very short puzzle question. It's like question 9, and that's pretty much going to be the end of this, and we'll move on to another section because things seem to have went pretty smoothly. Well, I'm basing that, in fact, I didn't get a lot of questions. I hope that's what it means. So, question 9. Oh, let's get those solutions out of the way again. I did that to check one of the answers, forgot to make it go away. Right. Find the equation of a curve that passes through the point 0, 4 and whose slope at position xy is x over y. that is actually a differential equation. It's not written the usual way, but it is. Now, right at the end is the key to the differential equation, whose slope at the given point is x over y. Now, the slope is dy by dx, and it's equal to x over y. The other piece of information is 0, 4. Basically, x and y. Another way of writing that is y of 0 equals 4. So let me take that question now and show you how it was transformed into just a typical variable separable differential equation. The slope was x over y. Check. The point that we know is the same as telling you this, right? X is 0, y is 4. Right. In the big scheme of things, wouldn't this be a very simple differential equation to solve? But for completeness sake, I'm going to do it. One half y squared, 1/2 x squared plus c. Multiply both sides by 2, and then take the square root. I guess technically I should be taking plus or minus, but let's just assume that it's positive. And that's the general solution to our differential equation. Done. Now, if you tell me y of 0 is 4, this is 4 when x is 0. So 4 is the square root of 2c, squaring both sides, and then dividing by 2, and I now have that. Now, we already know the general solution. One of these two is the right answer. But only one of these two. Is it number 1 or is it number 2? What is the correct solution to this puzzle? Here's the key. What number should this be?
Number 2.
Yeah. Notice how it says plus 2c. If c is 8, plus 2c is 16. Remember that earlier one where there was a minus c in the thing and you had to call the answer minus the thing, not just the thing? That's one of the little hiccups that you have to kind of be aware of. It's easy to forget. So I am going to do something really sneaky. I am going to ask you to say hi right now. And if you are here at 20 past, you will say hi. And if you've been going to watch a movie and coming back at the end of 2 hours, you won't have said hi, in which case you are not here and I am not going to give you attendance. Does that seem fair? Agreed? So if you ain't here, you ain't saying hi. And I am looking at 11 highs. 12 highs. Well done. 13 highs. There are 13 of you here, so only one of you isn't here. I'm not going to tell you who it is, but that's fine. No, that has actually cheered me up a lot. It just means that you're tired, and I totally understand that. But you are here and you are listening, so that's cool. I'm finished with this particular technique for solving differential equations. Is there anything about it that you want me to go over before I move on? Anything?
Can I see the last little bit again?
Sure.
Thank you.
Okay. Bit of history. Do you see these differential equations that we're doing right now? Do you know that Newton, you know, the guy, the apple from the tree, the gravity guy, he actually used differential equations to find the formulas that are used before Einstein came across for why planets or how planets orbit round the sun using gravity. And it's basically just a big ugly differential equation that when you solve it, you get planetary motion. That's how big this is. Well, I'm going to take a few moments to get myself organized, and then we'll come back. I'm not going to leave, I'm just getting some stuff here. And then we'll come back and we'll be starting the next section. Oh, time. I'm just looking up some stuff here. It'll take me a few minutes to get myself ready. It's good news. I wasn't expecting to get that finished today, but things are going really cool. Okay, I'm ready. So the next type of differential equation we're going to learn how to solve are called linear differential equations. So let me make sure that I've got the screen on. I'm never be sure what I've got on. There we go. So what does a linear differential equation look like? So there's this over here. A linear differential equation has the form. Where are dy by dx plus p times x, a function of x, y, equals another function, q of x. You'll also see it written like that. Now, if it's written like that, you will never be able to get a variable separable out of it, right? They are quite different. These linear differential equations have a function of x called the integrating factor.
Do those equal g of x at the end there?
Q's.
Q's, okay, sorry.
That's just the way I've written them. I mean, technically you could call it g of x and it would work. You just have to label them according to what you think makes more sense. And this thing called the integrating factor is e to the, I'm trying to write it down because I don't want to screw up here, e to the px dx. And actually, the integrating factor is this guy. And this fella is, darn it, I was right the first time. I knew I should have paused. it is called the integrating factor, and this fella is going to get us the solution eventually. Now, what I'm hesitating here because I already screwed up once. So let's just make sure I'm clear about this. A linear differential equation has the form derivative plus some function of xy equals some other function of x called q. These guys have a guy called the integrating factor, which is him. And this thing here is going to get you the solution eventually to your differential equation. And the solution is going to be y equals. Just checking the solution. No, they don't have it. Right. Oh dear, that's not good. No, never mind. I want you to take a 5-minute break and be back. And I am going to find the general solution to this. Now, I kind of know what it is, to be absolutely certain. And there is a QX, and I finally got it. Right, this is correct. There is a QX there. So essentially what we're going to do is you're going to get this guy. You're going to find who P is and who Q is. That will allow us to get the integrating factor. Once we know this, we plug and chug it into this formula. And if all works out, it should actually be a nice integral. So that's what I'm hoping for. So I am definitely not going to make up questions off the top of my head, because based on today, that probably won't work well. So here's question 1. We're being asked to solve this linear differential equation. So I'll now take you through the process of how to do this. Step 1. Rearrange the differential equation so that it is linear. Now, what does that mean? It means make sure this guy is y dashed. Make sure this guy is dy by dx. Make sure that you've got next to it so many y's, and then equals whatever the x's are, goes here. Now, in this particular question, it's actually it's already good to go, right? So that step didn't happen. But in general, that would be your first step. Right? Then you identify who is going to be your P of x and who is going to be your Q of x. P of x, in this case, is number -1. Q of x is that guy. Step 3. Find the integrating factor. E to the power of the integral of px dx. E to the power of the integral of -1 dx. E to the -x. Now, when you do the integrating factor, I know there's a temptation to put a plus c, but just don't. The integrating factor does not have any c's in it. Now, step 4. Use the formula to solve your differential equation. So the solution to this differential equation is given by this ugly formula. Y equals 1 over I of x, the integral of those two guys plus a c. Now, do you notice in this question, you already have the plus c? That means nobody else gets any other plus c's, right? That's the only plus c in town. Now, in this question here, that becomes 1 over e to the negative x, the integral of 8e to the x times e to the negative x plus c. Now, something really nice happened here. Do you see that e to the x and e to the negative x, when you multiply them together, gets you e to the 0, and e to the 0 is just 1. So what you've got is 8. And if you integrate the number 8, you get 8x plus c. And in general, you should try and make things look as pretty as possible. Would you agree that 1 over e to the negative x is kind of clunky? Wouldn't there be a nicer way to write 1 over e to the negative x?
Just e to the x.
Right. And now you are finished. Unless this question, which this one doesn't, unless this question had a y of 0 equals 10 thing, right? If it had this, wouldn't you just figure out what c is and that would be you finished, right? But here we're finished. This is the general solution and we are done. So it's really just a 4-step process, right? And maybe if you're lucky, you won't need to do step 1. Maybe. But pretty much you will do a step 1. So here's a second example. Y dashed equals 9x take away y. It's not in its appropriate form, right? Step 1. Don't I have to add y to both sides? Agreed? It has to be a derivative, check, plus something times y, in this case 1 times y, equals the x is on its own. Now step 2 would be identifying who your p is, right, and who your q is. And p is 1 and q is 9x. Are you happy about that step? P is whatever's next to the y, q is whatever is on the right hand side. Step 3, find the integrating factor. It's e to the power of px dx. It's e to the integral of 1 dx. It's just e to the x without any plus c's. Step 4, get the solution. 1 over ix, the integral of qx ix dx plus a c. 1 over e to the x, the integral of 9x e to the x dx add c. And here we've hit our little kink in the road. I need to integrate this, don't we? In fact, once I get the answer to it, it's just going to go in here with a plus c. But I can't do that in my head. I wouldn't try to. So let's do it as some working on the side. What technique will I use to integrate this guy?
Integration by parts.
Agreed. Do you recognize the shape? This is F, this is G. Do you recognize the integration by parts shape? Now I can imagine a different question. And this is what you got. Right? Can you imagine a different question? what would the technique be this time? It would not be integration by parts. What would you
U-sub?
do? You do a U-sub. Do you see that now you don't get told what to do? It's not every question is integration by parts. So you don't need to think about it because you know that's what you're going to do. Or every question is a U-sub, right? As now you get a question and it's just hanging there. You have to know the strategy to do it. So according to our formula, integration by parts is f, big G, the integral, take away f dashed, big G, dx. So you leave that alone and you integrate e to the x. You differentiate that guy and you integrate e to the x. And you now get that guy. Are we cool with where this came from? Right. Now, this fits in here. So this here, right, this integral is 9x e to the x, take away 9 e to the x. And now we are looking at our solution, our general solution, which is fine. I think I could do some style points on this question. Is there anything you think that you could do to make this look prettier?
Distribute.
Okay, if I'm going to distribute it, I could leave it that way, and that's fine if you want to leave it that way. And we get quite a lot of cancelling, don't we? And that is a totally acceptable answer. Would you agree that looks a little bit prettier? Another technique is, couldn't I call it e to the negative x? And distribute it that way. And I'd get this, which is an equally acceptable answer. Which one of these two were you thinking about when you said distribute?
The top one.
That one. Nothing wrong with that. It's the right answer. If WebAssign doesn't like your answer, it's not your fault. It's WebAssign's fault, because that is a totally acceptable answer. Are we cool about the process? We've got time for one last one. Right? Steps 1, 2, 3, 4. Move this guy out of the way. Last one coming up. Hopefully it's not question 3, but you never know. These questions vary so much, it could be. Guess what? It is question 3, or a version of question 3. Xy dashed plus y is 11 square root of x. Okay, step 1. This has to look linear. This does not look linear, but it will. What will I need to do to both sides to get this guy on his own, just to get a y dashed here? What will I do to both sides to get a y dashed here?
Divide by x.
Now that makes this a bit weird. I know it's divide by x, but can I just call it 1 over x? It helps. Now, what's going to happen if you divide this guy by x is you're going to get that. And if you're not sure where that's coming from, if you take this and divide it by x, can't you kind of half power it and get that? Are you comfortable? Divide by x, divide by x, divide by x. Me personally, I would call that guy x to the negative a half. Does that look better as far as powers go? So that's step 1 done, is now linear. Step 2, Identify who your P of X is and identify who your Q of X is. My P of X is this fella, and my Q of X is that fella. Step 3, find the integrating factor. E to the integral of Px. E to the integral of 1 over x dx. 1 over x is a log. But that is not the guy I'm going to write down, because I can simplify e to the power of natural log of x. It's actually a very simple thing, isn't it? E
X.
is just x. So step 4 is coming up, and step 4 is find the solution using this quite messy looking formula. So we have 1 over x, right? Integration factor is x. The integral of qx, which I've decided to write as a negative half power, times I of x dx add c. If you multiply these together, do you see that you get a positive a half power, right? An x to the negative a half times an x. 1 plus negative a half, you get a half. And then just going to do the power rule. Add 1 to the power. And then divide by the new power. So what's that going to get? It's going to get me 22 thirds. And if we distribute it, which is, I think, a good idea, right? That times that gets you this, that times that gets you this. And for really style points, shouldn't we call it a square root? This is the general solution to that differential equation. Well, we don't need to say hi because you've already said hi.